Let's see. Well, how about like this? Is that right? Okay, good. Well, good morning, everybody, again. As you know, the reason we started this college years ago, which is now about 6 years ago, was health. We found out that both exercise and moving our minds and keeping our minds active was a good way to fight Alzheimer's and lots of other things. So, come in. So the whole point of the college was health, and still is. And so today, we're going to stretch our minds by looking at the whole universe. And that'll stretch them. Come in. Let me get you some chair. I'll get you another one, just a second. That goes with it. So, the two handouts that you have are something that you can use with your grandchildren. The first one, this one, is an actual picture of galaxies. And when you hold it up to your grandchild and say, what do you think that is? They're going to say stars, normally. But it's, of course, both sides are pictures of galaxies. We have over 100 billion galaxies that we can detect already. Now, the universe is huge, and we're very small in comparison. Well, most of us. And the other handout is a fun thing for grandchildren too, and that is let them find out how much they would weigh on each planet, and even, Marvin, as we were saying, a neutron star. Marvin, how much would you weigh on a neutron star?
Well, I have to look at the data here. It would be, it'd be 29 trillion.
You don't look that heavy to me.
Well, I feel that heavy, though.
Yeah. Isn't that fascinating? And so you can have a good time with grandchildren with this data. Right? You see the picture up here. We're going to talk a little bit about this. Again, this happens to be a picture of the Andromeda galaxy. And most of the galaxies may not be as large as this one. This one is larger than our Milky Way galaxy, and it's our big sister, and it's going to come visit us in about 3 to 4 billion years. It's already heading this way at 28 miles per second. But it's got per second. But it's got a long way to go. It's over 4 million light years from here. So it's going to take it a long time. Our grandchildren won't even have to worry about that. Let's see. Marvin and I have sketched out a little skit here to show you how large the Earth is compared to the sun using a scale of 1 million miles equals 1 foot. Okay? So we measured it off going back this way. And Marvin, tell them how far down the hall we went. 93 feet. 93 feet. Right. So, and here is a marble. The Earth in this demonstration would be smaller than this marble. So would you hold the marble at least there? And imagine that he is 93 feet that way. And the sun would be right here. That's the scale of the Earth compared to the sun. Isn't that amazing? And we would be 93 feet down there, smaller than a marble. The Earth will fit inside the sun over 1 million times. So you thought you were a big shot too, didn't you? Okay. I think we've covered all the charts. Now, we've just had an amazing thing happen. It happened in 2015, and that was we sent out a spacecraft. If you find that for me, Marvin, there it is. The Horizon Space Probe. We sent that out to Pluto. Now, Pluto is 6.33 billion miles from the sun. Now, we're only 93 million. So Pluto is way out in the cold reaches of space. And this creature got there. It took it 9 years from the time we launched it to get there. And it was moving at 3,600 miles an hour as it traveled out to Pluto. And Pluto was going by this way around the sun 10,000 miles an hour. Now, how are you going to do that? Somebody can do math around here. That is, to me, one of the most amazing things that was ever done. Get that thing to go right by, and it came within 7,900 miles of Pluto, which is exactly where they wanted to take pictures. And when they took the pictures, what they saw was gigantic fields of frozen nitrogen, under which they calculated there's probably an ocean. You know, the oceans are all over the place in our solar system. If we backed up to Saturn and looked at Saturn's moons, I've got pictures of the moons here. These are some of the moons in the solar system. And if you go to Saturn's moons, which are, there's Neptune, Uranus, here. There's a very small one called Enceladus. And that one is covered with ice, and it has an under-ice ocean. So if Pluto's got an ocean, and Enceladus has an ocean, it's starting to look like a pattern, isn't it? Come all the way back to Europa. Big moon around, right here. Big moon around Jupiter. And sure enough, we think there's an ocean under the ice. That ice, by the way, is 15 miles thick. And that we're going to drill down and see if there's life in that ocean, because it looks like it's warm salt water. And it keeps warm because of the tidal forces of Jupiter. So that's going to be very exciting in just a few years. I hope I live to see it. They're going to drill down into that ocean. So that's the third ocean, even in our solar system. And of course, you come back to the Earth, that's the fourth ocean. Guess what? The sky's full of oceans. Because all of the solar systems may have oceans like that. Isn't that an interesting concept? Okay. right. Go ahead. The next slide. There's Pluto, and there's some of the big frozen glaciers of nitrogen. Nitrogen is very common in the solar system. What gas are we breathing? All right, nitrogen. Nitrogen. We're only 16% oxygen. We're breathing nitrogen right now. It's 78% of what we breathe. I do a lot of school programs, and I ask the kids, what are we breathing? Oxygen. They don't know that it's nitrogen. Okay, next. There's the Enceladus. That's the little moon around Saturn that has an ocean. By the way, we've actually seen water spewing out of the ocean, and we have pictures of it. Okay? And there's Europa's moon, and that's the one we're going to drill down through. It's probably the best chance of life out there in our solar system is in that ocean, because warm salt water. Okay. There's, of course, our own ocean on Earth. And now we have found a planet. Now, 70% of our planet is covered with water. But that only constitutes 0.5% of the mass of the Earth. The Earth is a big rocky planet, and the water's just surface. But we have found a planet now that's 70% water, which means that it's probably totally covered with water and no land mass at all. It's amazing what we're starting to find out in space. And that's just in our solar system. Let's go to the rocket. Marvin likes to travel, and we're going to put Marvin in that rocket. Well, racket's not far off, but rocket. And have him go to the next closest sun to our sun. And that would be something called Proxima Centauri. And that's 4.2 light years from here. So, Marvin, that's going to be the size of your trip to get there. Right? And you're going to be in that rocket for quite a while. As a matter of fact, I've got a new figure. I showed you one figure the other day. I've got a new figure that they've now calculated it's going to take Marvin 73,000 miles, 1,000 years to get there.
That's a number of generations, isn't it?
Yeah. How many generations you think that is? Isn't that amazing? That's the closest other sun. And that you saw on this, there are billions of them. And that's how long it would take Marvin to get to the closest one. It's amazing, isn't it? Yeah. Okay. This is an image of Neptune. Those winds blowing, that's one of the storms on Neptune that we've found, but the winds are blowing 1,500 miles an hour. 1,500 miles an hour. Now, if you and I were on the tee and we hit the ball, this one, no? And we had a 1,500 mile an hour wind behind us, Jim, how far could we hit the ball? Yeah. Jim, by the way, Dave, is a very good long hitter. But even he would be able to knock it out of sight, wouldn't he? And there's another really interesting thing about Neptune that they've discovered. It rains diamonds Now, Mary Lou wants to go there for some reason. Yes, you may go. Betty can go. Anybody else want to go? You want to go? Well, you go take the bus.
Only 14 can go there.
Oh, well, let's see. At least we know where we're going, and we know what's there. Yep. Isn't that amazing? And it turns out it also rains some diamonds on, let's see, I don't have a, where's my Saturn? Barely, did I give you the Saturn? No, I gave you Jupiter. Yeah. It turns out, yeah, it's supposed to look like Jupiter. It does. Jupiter rains diamonds also. And it's only 480 million miles from the sun. So it's closer. That thing there is over 2 billion. So it rains diamonds on Jupiter. Jupiter, by the way, weighs more than the rest of the planets combined. It's a whopping big planet. And you can't walk on Jupiter, Jim. You couldn't even tee it up. It's a big ball of hydrogen gas. And the pressure is so great, if you dove down through the clouds of gas on this, you would get to liquid hydrogen. It actually turns to liquid toward the core. It's an amazing thing. This thing has a diameter of 88,000 miles, and our Earth only has a diameter of 8,000 miles. So we're very tiny compared to this thing. All right, go ahead. That's the closest sun I was talking about. And I want to do some comparisons on size. Let's see what's next on the slide. Yeah, okay, dwarf red star. Let's mention that first. All right. Our home Milky Way galaxy, and remember there are billions of galaxies. Our home Milky Way galaxy has 100 billion stars. And 3/4 of the stars are what is called red dwarfs, or dwarf red stars. And those they're smaller than our sun. And it's interesting to me that most of the suns in our home galaxy, and as a matter of fact, the other galaxies too probably, are those red dwarfs that we can't see. So when you look at the sky at night, you can only see the brighter stars, about 5,000 visible through the regular. Now I have here my astronomy binoculars, and with these I can see a few more than we can with the naked eye, and I can see things like we're going to talk about in the Orion Nebula pretty well. But these things, Mary Lou gave these to me a few years ago. These things cost $500, even then. But if you look at the sky with some binoculars, you'll be surprised at what you can see, especially in the Orion Nebula. And we're going to talk a little bit more about the Orion Nebula in a minute. Yeah. The white dwarf star, by the way, is the future of our sun. So eventually, our sun will blow off the outer layer, and most of the stars do that in this class of stars. By the way, there are stars that would make, imagine this whole room as a star. Our star could be that small by comparison to some of them. when that dies, it will become a white dwarf. And a white dwarf will be very compact. Okay? Go ahead. Brown dwarfs are in effect kind of failed stars that didn't quite have enough energy in them. And all stars are caused by fusion of the hydrogen atoms. That's what turns a star on, when they fuse together. And we are trying to figure out on Earth now how to use fusion power. And it's very difficult to figure it out. We're working on it really hard, have been for years. If we could ever make that work, it would end the energy problems on the Earth. It'd be a tremendous breakthrough. Well, this is a brown dwarf star that didn't have enough fusion. Okay? All right? And some of them can even go to black as they're dying. Okay?
Are these dwarf stars all about the same size?
Yes, good question, Jim. They are about the same size, and they will be as small as the Earth, even. And we already saw how small the Earth is compared to a large star. Okay? Yes, they spin. They tend to spin. The ones that spin the most, do we have a picture of a neutron star? I don't think we have one. A neutron star would be white, and that's even more compact, and it spins 200. We have one that spins 217 times per second. So it's going bzzz, like, huh? Yeah, it's even hard for Jim to tee it up on. 217,000 times per second, the thing goes around. And the neutron stars are so compact that a thimble full would weigh several tons. Well, they're in their location relative to the gravity field that they're in. That keeps them where they are. But they also have great gravity attraction to it. You don't want to get near a black hole or a neutron star. Their electronic fields around them would just sweep you in. Okay, Orion. This is my favorite constellation. This is also called the Winter Constellation. And it has some tremendous features. Now, my binoculars there can see inside this area of Orion. And by the way, this is the basic shape, the 4 stars like this. In the middle here is called the Orion Nebula. And that nebula has enough gas and dust. You know, that's the way stars are formed. Gravity pulls gas and dust together. That has enough gas and dust just in that nebula to build 10,000 suns. And it's in the process of doing it, and we can actually see it happening. This star down here is called Rigel. It's 55,000 times brighter than our sun. It's a blue giant. And blue giants grow old fast and die. But they're the hottest kind of star. This one up here is Betelgeuse. The movie's named after it. Betelgeuse is an amazing sun. This one, the diameter of this one, well, first of all, the diameter of our sun on our scale was 1 foot diameter. The diameter of Betelgeuse is over 300 million miles. Can you picture something that large? And we can see it very clearly. It's the biggest red spot. It's 624 light years from here. And it's going to blow up into what's called a supernova. And when it does, it'll form probably a black hole or a neutron star in the core, because it compresses in and it throws this shell out when they blow up. And that's what forms the big clouds of gas and dust that start another generation of stars. And our sun, by the way, is probably a second or third generation star. Stars that died before blew up, and the gas, they were pulled together, reformed, and made our sun. And ours is probably a second or third generation. Explode.
In that time, does that take an hour or 2 hours, or does it take years?
That's a good question. The initial explosion would be very fast. It would be much less than a year. But the after effects that would spread all the way out could take millions of years. But the initial explosion part would be very fast. It'd be just like any explosion you see.
Does it become a neutron bomb?
It can, well, in a way, if it becomes a neutron star, it depends on the size. Okay, if it's 8 times larger than our sun, it will probably become a neutron star. If it's, say, 20 times larger than our sun, and their stars, much bigger than that, it could become a black hole. And we now feel, or know, from what we can calculate, that in the Milky Way galaxy alone, remember we've got 100 million galaxies. The Milky Way galaxy alone, we estimate now that there are 100,000 black holes, stellar black holes, ones left over. And they'll be about the size of Earth. But boy, when you get in your rocket ship and you start out into space, you don't want to get near one of those things. They are terrible. One way to understand a black hole is to compare it to a hurricane, which you could do better than I could, but the eye of a hurricane is a low pressure system. Is that right? And the stars, the raindrops going around it are like the stars. So a black hole is kind of like the eye of a hurricane, but it's a hurricane of stars. And we have what's called a massive black hole at the center of our galaxy. And most of the galaxies have a massive black hole. Ours is 4,000 times larger than our sun. That's a whopper. And you don't want to get near that thing either. If you start getting close to it, it will start pulling you in, and it's called spaghettification. Make you string out like a piece of spaghetti. You don't want to do that. No. Yeah, okay. All right, go ahead. This is comparing some of Earth's, our sun, to Betelgeuse. Look at the size comparison. Makes you humble, doesn't it, that we're on such a small system. Okay? And then our Milky Way galaxy. This of course, is an artist's version because we can't take a picture of it since we're in it. Okay? But imagine, though, that there are